Welcome back, my friends. We're talking about strain energy today. We're talking about our old friend, the stress-strain diagram, okay? So strain energy. What is strain energy? Strain energy is the energy inside of a material that can do work. What is work? Remember, it's a force moved over some distance, right? So it's a force times distance. It's Newton meters or joules. And so how do we get strain energy in material? Okay, so think of material as a big spring. Okay, so here I have a piece of actually it's a piece of a rubber glove, okay? So it's a stretchy material like a rubber, okay? If I start to deform this, it's going to build up some energy that could do some work. So let's just see what that looks like. I got my assistant here. Give me something to push against, okay? Here we go. So I'm going to push against the end of this broom handle here, and you can see that that is starting to deform. Now, when I let go of it, what happens? Okay? It goes right back where it started from. What does that mean? Okay? That means that we started deforming it. We started putting stress on it, right? Force over area. There was a force, I applied a force to it over the area at the end of the broom handle. And as I did, it started to elongate. It started to deform, didn't it? Okay? So we came up here somewhere, and then I took the pressure off of it. And guess what? It came right back down to zero. It returned to where it started from. Okay? Now, can I push on this a little bit harder? I don't know. Let's try. Here's my pushing thing again here. Here it comes. Okay, ready? I'm going to push on a little bit harder. Oh, that's pretty hard. I'll let it go. It is, I don't know if you can see it, a little bit deformed. It has a little bit of a bulge in it there that you can see sticking out of it, okay? What does that mean? That means that I put enough force on it to get past the yield point up here, right? Remember, yield is past the elastic region. So even though you think of this as being elastic because it's rubber, we have gone past its elastic region. So we were somewhere up in here, okay? And that point is the point where there's permanent deformation. So at that point, what do? Do you remember? We follow that line back on a parallel line to this guy, right? We follow him back down, and we can read the permanent deformation in that part. Now I'm going to there's another one that'll show up a little bit better, and that is something like this. This is just a piece of, this is polyethylene, a piece of a sack, okay? Let me do the same experiment on this little piece of polyethylene here. Let's see what happens to this, okay? So here we go. I'm going to push on this. Oh, wow, look at that. Man, it really deforms. Look how much it deformed there, okay? So on this one, what does that mean? That means that I didn't push on this quite as hard until it got here. So on this material, okay, it's something like this. I didn't push on it very hard before it started to deform. But then when it started to deform, it really deformed, okay? Now let's try one more time. Can you come back one more time? I'm going to push kind of in the same place here. Okay, I'm going to push with some force, and oh, what just happened right there? Okay, the energy that was built up in there, right? I got it all the way over here to boom, to fracture. Okay, this is fracture. Okay, we took it to failure where it poked a hole in my bag there, right? So this is a little more easy to see. This one has a little more strain energy. It will store more energy than that other plastic will, right? Because it acts like a spring. And why is it doing that? Well, think about those little molecular bonds in between those molecules are like little springs. So I was stretching those bonds, but not to the point where the bonds start to break, right? So when I let go of it, they relaxed back into a happy place, right? Into their crystalline structure where they like to live. And that's exactly what goes on in this material, okay? So strain energy is usually talked about in strain energy density. How much strain energy can a material take or absorb? And that would be in terms of work or energy, Newton meters, foot pounds, okay? And generally what that is strain energy is the area under this curve multiplied by the volume of the amount of material that you have. Because if I look at the area under this curve anywhere? For instance, let's just for fun here, not that much fun, right? Let's calculate the area underneath this curve right here, okay? What do we call that area right there, okay? We call that the modulus of resilience, right? That is the strain energy for a material to deform, but then when the force is taken off of it, it returns back to zero, right? There's no permanent deformation in that area. So that area there is 1/2 the base, right? And the base is strain. So the base here is 0.0030 times the height, which is 600, and that's in megapascals, okay? Okay, we call that U, strain energy there. Okay, now this is just strain energy. So this unit here for this is millimeters over millimeters, so it's basically a unitless. So when I multiply unitless times megapascals, the energy is going to come out in megapascals, or force over area, newtons over millimeters squared, right? So let's see what we get here. Where's my calculator? Okay, so 1/2, I should have done this in my head. Let me start over again. Clear. 300 times 0.0030 equals, so 0.9 megapascals is that area underneath that curve, okay? So U equals. Or we could say this equals 0.9 newtons per millimeter squared, right? Now, let's say that we wanted the strain energy density, right? And that is how much strain energy per unit volume do we have over here? And really, if you're really sharp here, you can figure this out. You know that the units have to come out in something like Newton meters, right? So how much strain energy can this guy take before deformation, or with no deformation, right? Because we're in this yield, this elastic region here, so no deformation. We need that in, we want it in Newton meters. That's a typical unit of work or energy. Okay, so this is in millimeters. So number one, how do I get that into meters squared? Oh, that's pretty easy, isn't it? So 0.9 newtons per millimeter squared equals, there are 1,000 millimeters squared per meter squared, right? So I'm just turning this into a Newton over meter squared. And so what is that? 0.9 times 1,000 squared equals a lot. So U equals 900,000 newtons per meter squared. Now, if I find the volume of this, right? So I'm going to take my energy, my strain energy, and I'm finding the strain energy density. Okay, so this down here is going to be energy density. Okay. If I multiply that times volume, right? And let's say the volume is in meters cubed, then what are the units going to be? 2 of my meters cancel out, and it's going to leave me with Newton meters. That's the unit I want. So you can, if you don't know how to do these problems, if you just let the units work themselves out, you can't hardly get it wrong. So here's what we're going to do. We're going to take 900,000, okay, newtons over meter squared, and we're going to multiply that times the volume of our specimen. That's what our specimen looks like, okay? So what is the volume of that? It's pi r squared for that area times, whoop, the height, right? So times, and those are in millimeters. We want everything in meters, so let's put this in meters. So let's see, 600 is 0.6 meters times the area, which is pi times r, 7.5, but that's millimeters. So in meters, that's 0.0075 meters. One more parenthesis, okay? So 900,000 times 0.6 equals times pi equals times 0.0075 squared, pi r squared, right? equals 95.43. 95.43 Newton meters, okay? And that would be the energy density that that material can store without deformation. That's the maximum amount of energy density that specimen can store right there. So it's the area under the curve, okay? The modulus of resilience, that's right, times the volume of the specimen gives you the energy density. That's all there is to it. Now what we're going to do is we're going to work a bunch of problems off of this one stress strain diagram, okay? This one diagram. How many problems can you work? I know you've probably already seen what's going on over here and it's scary. Well, there are 9 things. Let's see if we can work through these. Okay, so using our stress strain diagram, let's see if we can answer those 9 questions about that chunk of material right there, okay? Number 1, what's the elastic modulus of the material? The elastic modulus is E, okay? And it's defined as the slope of the line here on our graph, right? Our stress strain diagram. And how do you find slope? Easy. Rise divided by run, right? So the rise is 600 megapascals. In other words, it's sigma over epsilon, isn't it? 600 megapascals divided by the run, which is 0.0030. Okay, so what does that equal to? Let's see. 600 divided by 0.0030 is 200,000. Or 200 times 10 to the 3 megapascals, okay? So there is the answer to part A. So what does B say? Or B, number 2. With a factor of safety of 2, find the largest force without deformation. Okay, so without deformation, that means that we got to stay under sigma yield, doesn't it? I got to stay under here. So as long as the force goes all the way up to there, and you can kind of think about this as the force applied, and this is the amount of deformation or stretch that comes from that force, right? So, in other words, what is the force that causes that number there? Okay, let's see if we can find that. So the first thing we got to deal with is this factor of safety of 2, okay? So what should we use as sigma for no deformation, okay? Should you use 600? No. 600 is a factor of safety of 1 because 600 divided by 1 is still 1, right? So what that means, factor of safety, what does that mean? We talked about that in an earlier video, that I want to make it twice as safe as it needs to be, right? I don't ever want to get to the deformation, so I don't want to get to 600. If I want to make sure I don't get to 600 with a factor of safety of 2, that means I need to divide 600 by 2 so that I stay down here at 300. That way I am really safe, right? That's kind of way you got to think about this. Because think about it, if I multiplied 600 by 2, what would I get? I'd get 900, which is, this material can't even take 900, right? It's way failed, okay? So factor of safety of 2 means I divide my sigma by 2, okay? So sigma y divided by 2 equals what? 300 megapascals, okay? This is for part number 2. This was part 1, okay? So 300 megapascals. What is sigma? That's sigma, right? What is that? That's normal stress. What does normal stress come from? Well, it comes from the force over an area. And our area is what? Pi times 7.5 millimeters squared, right? So take 300,000, multiply it by that, and I have F, right? Now, what is this over here? What is this? Megapascal is really a what? A Newton over millimeters squared, right? So when I multiply the other side by millimeters squared, those are going to go away, those are going to go away, and it's going to leave me with newtons. So F is going to be in newtons, right? Okay? It's important that you get these units figured out. So 300 times pi times 7.5 squared equals 53,014. So this F equals 53,014 newtons, or F equals 53.0 kilonewtons. Okay? So there's the answer to number 2. Let's see what number 3 has for us. What tensile energy can the rod sustain? And I should have written, I didn't write it on here, without permanent damage, okay? Without permanent damage. In other words, without permanent deformation. And you know what? We already answered that one, didn't we? There it is right there, in Newton meters, right? They want it in Newton meters. We already got that guy. That's number 3. We did it ahead of time. I am so sorry. Number 4, what max tensile load, what force P can we put on the rod before it's sustained, or how much, let's see, what max tensile load can the rod sustain before fracture? So we're trying to find a force on the rod. What's the biggest force we can apply to the rod before, bam, fracture happens, okay? Where does fracture happen? At 450, right? So 450 is sigma fracture. And remember, this number is engineering number. It's an engineered number, okay? It's not the actual number, because you don't put less force on it to make it break, okay? The reason this goes down over here is because this region over here is called necking, right? And we assume that cross-sectional area doesn't neck. We keep that cross-section constant, and that's why that graph goes down, because the area, engineering area, doesn't ever change. It does in real life, but it's really hard to know how much. And so we just go down like that. We hold the area constant. So 450 megapascals, and they're asking me what force causes that, okay? Pi r squared, right? So same as the one above up there, okay? So that's going to be what? 450 times pi times 7.5 squared equals 79.52. Okay. Did I write megapascals? Is that right, megapascals? This is newtons over millimeters squared. This is millimeters squared. So when I multiply that, the millimeters cancel out just like it did here. That's not megapascals, is it? No, sir. That's newtons, isn't it? And I moved the decimal over 3 places, so that's actually kilonewtons, okay? Just like we did here. And you're like, wait a minute, how come that's less? Oh yeah, this was 300 because of the factor of safety of 2, right? So this should be bigger, okay? So F equals, and that is for number 4. Okay, we're almost halfway here. Number 5, while under a tensile load of 2.25 times 10 to the 4th newtons, the rod will elongate how much? So how much is this thing going to stretch? It started off at 600. What's its new length? Let's see if we can calculate it. All right, so I erased my board. We still got all our answers over here, but let's see if we can do this. So what do we got here? We got a force, right? Let's divide that force by an area and let's get us a sigma, shall we? Okay, so 2.25 times 10 to the 4th newtons. 2.25. I'm just going to move the decimal over 4 places, right? So 2.2512. That's 4 places, right? 1, 2, 3, 4. Okay, so 22,500 newtons divided by the area, which is pi times 7.5 squared. That's millimeters squared. Newtons over millimeters squared is going to give me megapascals, which I need for this scale over here, right? So 22,500 divided by pi equals divided by 7.5 squared. 7.5 squared equals 127.32 megapascals. 127.32 megapascals, okay? So that's what sigma equals with that kind of load on it, okay? So how much does it elongate? Here's what we got to do. Let's look at our graph over here. Let's see. 100, 200, 300, 400, 500, 600, 700. So these are 100 apart, right? So we need to go 127 with it, which is like there, okay? And this is kind of you may get a slightly different answer than me because we're reading it off of a graph. We're making our best guess of what this could be. Now, we don't have to make a guess at all, do we? Because, why? What is that number right there? Okay? Well, I could guess it's less than 0.001. There's 0.0005. So I'm going to say like 0.007-ish, right? But how can we get it exactly right? Similar triangles, right? So here we go. Since we're on this same slope line, right, we could say 600 megapascals is to 0.0030 as 127.32 megapascals is to, I don't know, X, right? So what is that value right there where question mark is? Well, I'll tell you what it is. So X equals, here we go, 127.32 divided by 600 equals times 0.0030 equals 0.000637. Hey, we were pretty close, weren't we? 0.000637. And what is that? That's millimeters per millimeters, okay? Is that how much the thing stretched? No, that's how much each millimeter of it stretched. How many millimeters of it do I have? 600. So I have to take that number, right, and multiply it times 600 equals the total stretch, because it asked me that, right? The rod will elongate by how much? Well, here it is right here, number 5. The rod will elongate, I'm going to put a little delta there, 0.382 millimeters, okay? That's it. So this number is strain, but it's millimeters per millimeter. So if I want the total, I have to multiply it by how many millimeters I have, right? Does that make sense? Let's try number 6. Number 6, while under a tensile load of 2.25 times 10 to the 4th, same load we had there, right? The rod's diameter will decrease to what? Okay, the rod's diameter is going to change. Now, what does that mean? Okay, that means that as I have a specimen here, let me put it this way, as I start to stretch on this specimen, it grows in length, but what happens to the width, right? This part here. As I stretch on this, it starts to go this way, doesn't it? So as I get a deformation one way, I also get a deformation, we'll call that longitudinal, right? This is longitudinal along the axis. This is what we call lateral. So there's a lateral and a longitudinal change when there's a deformation, okay? You know what that sounds like? Poisson's ratio, right? What is Poisson's ratio? Poisson's ratio is negative strain lat divided by strain longitudinal. Okay? Now we're given Poisson's ratio for this material is 0.35. So do we know what, at that load there, at 2.25 times 10 to the 4th, do we know what the strain longitudinal is? We just calculated that, didn't we? The strain longitudinal is that right there, isn't it? Okay? So how do I find the strain on the lateral, right? This is longitudinal, right? So what are we doing here? We're compressing a tensile load, right? So we're stretching this thing. So the diameter, is going this way, isn't it? Okay? And so this is long. And just think about along the axis, right? Longitudinal, long is along the axis, and this is lateral. Okay? So, this kind of is easy, isn't it? We got Poisson's ratio is 0.35 is equal to strain lateral, okay? And I'm just gonna, there's a negative in there. Why is there a negative? Okay? Divided by strain long. And we know strain long is right there. 0.000637, okay? Why is there a negative? Remember, strain lateral is going to be shrinking, so that's a negative number. So negative times a negative just turns it back into a positive number because Poisson's ratio is always positive, okay? So let's multiply that. What'd you get, calculator? I got 0.35 times 0.000637, okay, equals, so strain lateral, and it's going to be negative, which means it's shrinking, is 0.000223. Okay? And that's millimeters per millimeter. What do they ask us here? The rod's diameter will decrease to what? So what's its new diameter? Okay? What was the old diameter? The old diameter was 7.5 times 2. It used to be 15, right? So 15, how much did it decrease by? That much millimeter per millimeter. And I had 15 millimeters of it, right? So 15 times, answer, it's going to decrease negative, it's going to decrease 0.00334425 millimeters, right? So I'll just subtract that. 15 is what it started out as, and I'll just subtract minus answer equals. So it's new diameter. The new diameter, part 6, is 14.9967 millimeters. Okay? There you go. You see where that comes from? All right, that's number 6. Let's see what we got next. Number 7. The maximum energy sustained before fracturing. Okay? And again, in Newton meters, before fracturing. What's that all about? Let's erase the board. Okay, so this is another energy density problem. How do you know that? You can tell it just by looking at the units, right? So how do we do that before? Now, before fracturing, that means we're going to have to calculate the total amount of energy under the curve. So we want the whole, everything, okay? So how do we do that? I think the easiest thing to do first is calculate the area, because what are we going to do? Once we get the area of the curve, what are we going to do? Do you remember? We're going to multiply it by the volume of that thing, right? So that's all we got to do. So let's first find this area under the curve, okay? So the area under the curve is 1/2 the base, 0.0030, times the height, 600, okay? So there's the triangle part, right? Let's go over to the next bit. I think I would just divide it right down the middle here and make a rectangle out of that, and then there's a rectangle here, right? So we'll add rectangle, rectangle, triangle, triangle. Okay, I think it's the easiest way to do that. Okay, so this rectangle right here is how big? That's 0030, that's 0050. How about 0.0020? Okay, that's the width times the height, which is 600 megapascals. Okay, so if this is piece number 1, this is piece number 2, here's piece number 3, piece number 4, and piece number 5, okay? So piece number 3, the width is 50 to 70, so again, 0.0020, times the height, which is 450. Okay, there's piece number 3. Piece number 4, the width is 20, okay? 1/2 the base times the height. And what's the height of that little guy? The difference between 600 and 780, okay? 180. Okay? Piece number 1, 2, 3, 4, and number 5, which is 1/2 the base, 0.0020, times, what's the height of this guy? The difference between 450 and 780, which is 330, right? Okay? Let's add all those areas together, shall we? And that's all going to be in megapascals, isn't it? Okay? Unitless megapascals, unitless megapascals, unitless megapascals, right? Here we go, on. So, 300 times 0.0030 plus 600 times 0.0020 plus 0.002 times 450 plus 90 times 0.002 plus, what is that, 150, 165? 165 times 0.002 equals 3.51. Okay? Remember, we calculated before, just this area right here, it was 0.9 megapascals, right? So the whole thing, that sounds about right. So you got to make sure these numbers make sense in your head. Remember, that's newtons over millimeters squared, so we're going to multiply that by 1,000 squared to give us newtons over meter squared, okay? So times 1,000 squared equals 3,510,000. So 3,510,000 newtons over meter squared. Okay, that's U. Okay, now we're going to take that number and do what? Multiply it by the volume. Okay, so times the volume. We should have wrote this number down and we had already had it, but I didn't. So here we go. 0.6 meters times 0.0075 meters squared times pi, right? Pi r squared, okay? So times 0.6 equals times 0.0075 squared equals times pi equals 372.16 Newton meters, right? This is meters cubed. So all those two go away and leave me with newtons times meters, okay? So there's number 7. 372.16 Newton meters. Okay, we're almost to the bottom. Number 8. How many questions can you ask about one stress strain diagram? A lot. Number 8, the energy to deform it to ultimate stress. Okay, to ultimate stress. Well, it's kind of the same thing, isn't it? To ultimate stress is going to be areas 1, 2, and 4, isn't it? So we can do the same thing, but let's get rid of number 5. Get rid of that guy. And we'll get rid of number, what else? Number 3? Yeah, number 3. Goodbye, number 3. 1, 2, 3, right there. That guy goes away. So this is to ultimate, right? Now we just add that bit up. Okay, so what do we got there? I'm going to leave this part because I know we're going to need that, aren't we? Okay. All right. So let's see. Here we go, calculator. Woo! 300 times 0.003 plus 600 times 0.002 plus, what do we say, 150, 165? 165 times 0.002 equals 2.43. 2.43 megapascals times 1,000 squared equals 2.43 million, 2,430,123 newtons over meter squared. Same volume, right? So times 0.6 times pi equals times 0.0075 squared equals 257.65. 257.65 Newton meters. There's number 8. One more to go, gang. One more to go. Okay, number 9 says, if you load it to 12.4 times 10 to the 4th newtons, okay, so P equals 12.4 times 10 to the 4th. 1, 2, 3, 4, right? 1, 2, 3, 4. Yeah, 12.4 times 10 to the 4th newtons. What is, and then you unloaded it, okay? You loaded it and then you unload it. Find the permanent deformation. How much permanently deformed is it, okay? So here we go. So let's find out what the stress is, okay? So let's divide our force by what? By area, 7.5 millimeters squared times pi r squared, right? Newtons over millimeter squared, that's megapascals. So 124,000 divided by pi equals divided by 7.5 squared equals 701.7. 701.7 megapascals. Okay? Oh my. So we're up here at like 700 mega. So let's just go up here to 700. 1, 2, 3, 4, 5, 6, 7. Okay, so we are right there, gang. What does that mean? We are permanently deformed, doesn't it? Okay? Not we are, the specimen of the material. We're beautiful. Okay, so now, if I keep it under load, right? If I keep it at that 12.4, right? Then what's the deformation? I could go down here and I could read it off, right? Okay, but that's not what happens. It says I'm loading it and then what? I'm unloading it, okay? So when I unload it, it's going to follow that same curve back down, okay? Whoop. Okay, so a parallel line. This curve and that curve are parallel. And so here's where it's going to come out to, okay? To that number right there. Okay, can we figure out what that number is? We could do some geometry and figure that out, couldn't we? Well, it all comes down to kind of an estimation here, right? So this is 700. So I think the easiest thing to do here is use similar triangles, right? So I've got one triangle, my original triangle, which was 600 by 0.0030. And then this other triangle over the top of it goes all the way up to 700, doesn't it? Then I could calculate what this distance is down here, right? Which would be this length right here. So if I come down from this guy, this looks like right in the middle of this box, okay? So I'm going to say that that right there was let's see, this is 0045, so 0.00425 right there, okay? So I can subtract that length off of there and that'll tell me what this number over here is. Let's do a little similar triangle calculation right quick, which says 600 is to 0.0030 as 700 is to what, right? X. So 600, clear. 700 divided by 600 equals times 0.0030 equals 0.0035. So x equals 0.0035. Now if I take 0.0035 and I subtract it off of that guy, that will tell me what this guy right here is, okay? And just looking at the graph, I'm expecting it to be about 0.0007-ish, right? So let's see, 0.00425 minus that length there, which was my answer, is 0.00075. So this strain equals 0.00075. That's about what we thought it was, right? So I'm happy with that answer, okay? So what do we do now with that? What do we do with that number? Okay, so what you have is this. This right here is permanent deformation. That right there, permanent deformation. What about this right here? What is all of that over there? That is called the elastic recovery. That is how much the material recovered in inches per inch, right? So that's the elastic recovery. This is the permanent deformation. So that thing deformed, we stretched it too long, right? This is like your slinky, your little sister stretched, and it didn't go back to where it started from, right? And it stretched, the permanent deformation is 0.00075 millimeters per millimeter, and how many millimeters of it did we have? 600. You always multiply by the original length, okay? So 600 times 0.00075 millimeters per millimeter, right? This is, the 600 is in millimeters. So our deformation is going to be in millimeters. So here we go. 600 times 0.00075 equals 0.45. So that thing deformed, the permanent deformation was 0.45 millimeters. So delta equals 0.45 millimeters. Or you could say, right, the thing started out at 600 millimeters and now the thing L, nu, is equal to 600.45 millimeters, okay? Okay, so that's a good review over problems that could be asked about the stress-strain diagram related to strain energy. I hope all those examples made sense. I know this is a long video, but this is something students really struggle with. So I hope this helps you, and I'll see you on the next video.